Today's video should be super short and pretty understandable. We're going to be talking about what happens when there are multiple substituents on an aromatic ring. Of course, we're limiting this still to an electrophilic aromatic substitution discussion, and eventually we'll start to build in this week nucleophilic aromatic substitution. Well, the good news is that if you have that list, which I'll include as a screenshot once again, that's available as a resource guide from last week, this is all very understandable. I tried to set up a couple of different situations with two substituents. All the ideas that I talk about today are going to be consistent with when you have 3 or 4 or 5 substituents. One of the great things about that list is it kind of ranks everything in terms of activating ability, right? And we know that when something is activating, it directs ortho and para to whatever the incoming electrophile is. We also know that in general, if you're a deactivating group, that you direct meta. The one thing that I will say, and this will be important when we get to aromatic synthesis eventually, is that you usually try to kind of start with the more activating and work your way towards deactivation. And obviously that's just to make your job a heck of a lot easier. But another concept that we have to keep in mind is that usually activators are kind of a little better at directing when there's any kind of competition between, like, maybe one group directs one way and another group directs another. So probably the best way to do it is to just learn about it in these 3 different examples. I tried to pick out a couple of different groups so we could practice with how activating or how deactivating they are. Also the whole idea of ortho, para, and meta directing. So if you remember nothing about the list, keep in mind that if you've got a lone pair of electrons somewhere on an atom that is directly attached to an aromatic ring, that I can't think of a situation where that wouldn't be an ortho-para director, right? Anytime you've got some sort of multiple bond that's next to the ring, that is going to be some sort of deactivator and also a meta director, right? So our real job, if we just consider this first case here, the substituted aniline, or I guess substituted benzoic acid, is to recognize which of these groups are the most activating, because that'll become important eventually. And we're also going to try to label the positions that in some sort of synthesis would deliver an electrophile pretty effectively. So let's switch over to, let's say, blue. So we look at this, we recognize that a mean group is going to be trying to direct to ortho and para to itself, right? And so that group alone, if I look at these blue check marks, right, these are the 2 positions that I'm going to deliver some sort of electrophile to. You'll notice that that position is blocked by the carboxylic acid group, so there's not much I can do about that. So just looking at that amine, right, that's where I'm going to see an introduced electrophile. Let's look at this guy. We'll recognize, okay, so that's going to be a deactivator, right? And in a sense, right, we're hitting with a lot more gas in terms of activation relative to this as a deactivator. It's a fairly strong deactivator, but that's a really, really strong activator, right? And so, like, the overall reactivity of this thing is going to be attenuated slightly, but the good news is that this thing is going to direct meta to itself. And so let's do that in red, right? And what you'll notice here is my check marks are all in the same location. And really, that's the goal for some sort of synthesis. If you were trying to design something, you want to kind of build in all those groups saying to the new group that comes in, go to that exact position. And of course, we know that there's not any easy way to select between these. I kind of alluded to that in the first video. You know, sometimes this ortho position is a little bit more sterically hindered here. It doesn't really matter. And so we might get a little bit more of this product. There's also examples where you can deliver groups specifically to ortho, and that's more of kind of advanced organic chemistry it's kind of outside the realm of this class, but just be aware of that. So for us, right, we're going to get an even mix of the new electrophile kind of going in those 2 positions. Good news is that we don't end up with a crazy mix of anything other than those. So let's go over to this other system here. I also, in this case, picked an activator and a deactivator, right? But this time, there's a little bit of I guess, a problem that we have to confront, right? If we look at this topmost group and consider that thing as, okay, well, that must be an ortho-para director because it's got that lone pair of electrons. And let's use blue like we did for that position last time. That group is going to try to deliver things to the ortho and para positions relative to itself. But then we've got kind of this weirdo problem, right? We look at this thing, this nitrile group, which is a meta director and a deactivator. Well, that's going to try to activate meta to itself. Well, there's not really a problem there because there's an OH group already present, so that we don't have to worry about. But the problem is that we're kind of, in a sense, we're mixing our signals a little bit here, right? We've got one group that's trying to pick out these positions. We've got another one that's trying to deliver there. And of course, this will happen on occasion, but the one thing that we want to incorporate into syntheses is kind of simplicity. This is not super ideal. Yes, if you were to do a reaction, the electrophile would very likely end up in either of these places. That one might be a little bit less accessible, but we'd probably end up with some of it. And so in that sense, usually, the activators or the blue checks that I'm showing you kind of outperform the other, but that's not to say that there won't be a little bit of the other one that is produced. There's certainly not going to be much of it, but again, if you're really trying hard to do some sort of synthesis, which is the whole point of doing a lot of this, is you don't want to mix the signals where you can, do so. So that might affect kind of the order of by which you introduce groups. And we'll talk a lot more about synthesis, I believe, on Friday, and kind of ways that we can kind of turn on or off certain groups, which is pretty clever. So the last one that we'll talk about today is this guy right here. And what you'll notice is an interesting situation where we've actually got two activators. So this thing is going to react fairly quickly, but the problem is that we're going to notice that these guys are kind of mixing and matching where the group is going to go. So this guy got a lone pair of electrons, so it's going to direct ortho and para. And since I used the more activating group in my other two cases were blue, let's keep with that. You notice that the para position relative to this thing is blocked, right? And so I don't need a blue check mark there. Then I look at this alkyl group, and we remember that these groups are slightly inductively stabilizing of whatever the transition state is. So they're very slightly activating, they're very slightly ortho-para directing, and you'll notice that it kind of sets up a similar situation to what we had here, where one group is trying to put in an electrophile in one spot, another one's trying to put it in a couple other spots. And I will be honest, that would be bad mamba jamba in a synthesis, but usually the majority of product is going to end up with doing some sort of ortho substitution somewhere on those blue carbons as opposed to the red ones. So as I said, we can, by kind of working in that list, when you do your homework, make sure you have that list right there. So there's kind of like generalities that we can kind of be pretty solid with, right? Whether or not something is an ortho or para director or an activator or deactivator. The things that sometimes make things difficult in more complex questions are kind of which one is more activated, how hard am I pressing on that gas pedal and how hard am I pressing on the brake pedal? And that's something you may want to just kind of, have that list out for to kind of get a little bit of a sense of that. So that's it for today.